The presentation is not. ठीक है. Okay, let's work this. Okay. What? Azimuth or little. हाँ? थोड़ा हाँ, good idea. इधर क्यों बैठ? टोकला. Just want to know which you are taking off. Not currently. Person, you have the molecule. You need a mic. Like it's been a little. But they are still too much. If you can hear anything here. So like you can. Fourth years. Why are you graduated here? So fourth year, third year, fourth year. Years in your book. First year and fourth. You can just say hi. I just want to know what knowledge. Second year. Oh, I'm second year. So at any point, if you think you cannot understand something because you don't know a certain factors, okay, let me know. You can stop me and let me know, and I will. Oh, never got it. So, everyone, today's talk is the title for today's talk is Laboratory Astrochemistry Techniques for Investigating Kinetics of Reactions in Space. The speaker is Aditi Pradhan, integrated MSc, and she will start with her talk. He has done her PhD internships on studying the atmosphere of Venus. Who you are going to talk about? So, so I was saying this laboratory astrochemistry techniques specifically for measuring gate kinetics of astrochemically relevant reactions by the yeah. So most of this work is in with respect to the work done in the University of Rennes by Dr. Ian Sims and his group at the IPR, and yeah, you'll be getting now. So if you have read my abstract, if you haven't, there are different regions in space to be on. But this talk is mostly about reactions going on in the cold and dark regions of space. So the temperatures in these regions are very low, 10 to 15 Kelvin, 10 between 10 to 150 Kelvin. There are over 200 molecules, ions, atoms that have been detected. So if I were to ask you to make a rough guess, what do you think is name a molecule you think exists in space? Anything. Molecule. And it's a molecule. Okay. You can throw random ones. You know what? Carbon monoxide is very abundant. Here is an atom. Hydrogen is the molecule I never seen. Yeah. Okay. If I were to tell you, okay, I hope everybody does since your second year you're fresh. Everybody remembers the structure of naphthalene. So if I were to tell you that naphthalene exists and falls at that low temperature, just off the bat, do you think that's possible? Do you think it is? What if, like I say, a carbon 12? What is the possibility that a carbon 12 change that big of an of a molecule exists. Yeah, you can say it exists. Well, it does. In fact, even polycyclic aromatic hydrocarbons are the molecules that are being sought after right now. There is a race between two specific groups, one in the US and one in Spain, who are using their own radio telescopes to just detect new molecules every year. About 3.8 is the average number of molecules we are detecting per year right now. And most of them are polycyclic aromatic hydrocarbons, like naphthalene, benzene. There's a bunch of that, especially in molecular clouds at these low temperatures. So then that obviously leads to several questions. So where do these molecules come from? It's very low temperature. You do an organic reaction in the lab. That takes you probably some heating, right? Nothing in the organic lab really forms on itself. It's extremely low temperature. Where are these molecules coming from? What kind of reactions are going on? How are their concentrations being sustained? There's a bunch of questions. To give you a better flavor of, say, one of the questions that was actually addressed using this apparatus I'm going to talk, it's called the pressure is the following. So HCl and HNC, both isomers are fairly abundant in molecular clouds especially. In fact, what is commonly observed is HCl is more stable as an isomer, HNC is not. But HNC's population is much higher at lower temperatures than HCl. Whatever is happening there is so well correlated with temperature that the population ratio of HNC by HCl is used as a thermometer for, it's an astronomical thermometer in some sense. You can look at the ratio and comment on what the temperature is around. The point is that if HNC is indeed the unstable isomer, why is there more of it? And where is it going when the temperature is high? Is it just the temperature that's killing it? Are we really right in our prediction of temperatures around places? There are questions like this. All of these can be addressed. In fact, this has been addressed already. This and they use this apparatus which they built themselves to address questions like this is a very specific example, but the greater question I want to put out there, address today, is how do we even start thinking about these things? Like, how do we begin to answer these questions? What's the methodology behind, actually starting to recreate these space reactions? So the answer is obviously I don't know what is happening. How do I stop? Okay, so the answer is has led to the discipline of okay. Get back there. So the answers really have led to this really interdisciplinary field of astrochemistry. So astrochemistry has three okay, has three parts to it. Observations, laboratory astrochemistry, and modeling. So modeling is essentially when you put in a lot of reactions and try to put great constants in them and try to model the say atmosphere of a planet or a certain region. Whatever you conclude from there, you try to match best like any other model. You might match best to your observation. And if you get as close as possible, the theory that you're thinking or the abundances that you're considering are probably correct. So, but then modeling cannot proceed on this thing. Can I get a mouse or something? Yeah, I think I should connect it. I know content of the talk. Well, so astrochemistry is like the practice. Modeling, there's observation, there's laboratory activity. So modeling is what you know as you set up a bunch of equations, just like in other kind of modeling, chemical modeling is where you put like chemical reaction. And then you give them certain rates and you feed products of one reaction into the other, and then you try to recreate the parameter that you're actually observing. So the thing is that these parameters, you can't go to space, even if you know that something is forming, you can't really go to space, sit there and watch it happen, right? Or measure the rate. So that's where laboratory astrochemistry steps. There you perform experiments mimicking the conditions in space to figure out what the rate constants are and what branching ratios are related to what these things are. The aim obviously is to be able to model a region of the universe as like well as possible, so you understand exactly how the chemistry there is involved. Yeah, of course, laboratory astrochemistry also contributes to observation. So when you hear a claim of just like I said that there is nothing, do I how come you measure it? They get a very normal spectrum out of space. And then you repeat these measurements, this spectroscopy measurements in a lab. And then you match the lines, and that's how you know where how these molecules are or what these molecules are. That's how an observation works. So laboratory astrochemistry is kind of lab experiments sit right in the middle of observation and modeling. What we are concerned with is these branching ratios and rate curves because we want to measure the kinetics of the event. So this what are branching ratios and what are rate constants. I think everybody knows what a rate coefficient is here. Branching ratio is when you have a reaction say A plus B, you can have multiple pathways that you go. The easiest way to think about it is in terms of time in recursion. But the other easiest way to think about it is really say you do an organic reaction of you're trying you take a benzene and then you try to put two OH in, OH ions in. So you can have an ortho, a para, and you have an orthomolecular beta and a para. and these are different conformers of the same thing. They are all going through different reactions. Quantum approach onto the benzene molecule must have been different. So measuring rate coefficients is still easy in the sense that you can measure one molecule and just you can see one side of the reaction and see how it is declining in time, and that gives you a rate coefficient. But to actually measure branching ratios can get really complicated because you are measuring these, you need to somehow differentiate between the relative abundances of these very similar molecules that are just maybe rotational conformers, structural conformers in these. So you need a technique that can help you do. So from this point on, the way we are going to talk about this is we are going to discuss the technique in questions and answers. So we know what the problem is. We need to go down to really cold temperatures so that we can do these and get parameters relevant to astrochemistry. And we need a very sensitive detection technique so that we can measure branching. These are our problems. So now I'm going to throw you the problems and we'll see what kind of detection techniques you come up with. Or in the sense of instead of my idea being I don't want to dump this information on you about what these techniques are, but rather we'll have a discussion of what you think could work. Who knows, you might come up with a better technique out. So we'll go step by step into understanding why these decisions were taken into developing these techniques, why we need such specific techniques at all. So we'll start every part of this technique with a question, and then I'll answer with what they have built to, kind of resolve this issue. So firstly, we are discussing how to create the condition. What are these conditions? A 10 to 150 K cooling that is needed for the gas reactions. So what do you guys think? How if I were to tell you tomorrow, cool down your system to 10 to 150 K, like a reaction happens, what's the first thought? What kind of cooling technique would you? Helium. Helium gas is right, but like I think you mean to say liquid helium, like you would set up these are gas elements. Just want to put a gas in liquid helium. Really powerful freeze. A really powerful freezer. And then how will you do? How will you represent the kinetics of sitting inside the freezer? No, I think would you set up freezer? Yeah. You want to put everything in a fluid freezer. Doesn't have to be. What is your yeah? No, it has to be fluid. What kind of detection technique is it in? Physics will like can be divided submerged in helium, like the sample is submerged in helium, liquid helium. There are two. You're doing a gas phase here, so you have to put gases to helium. Okay, fine. Okay, I agree. Let's take helium and put our whole chamber in helium. These gases, if you put it down to that cold of a temperature, these gases will start sticking to the wall. We can't have that in such time. That's not allowed. So that I get all these weirdly weird problems. The volume cool gas. How do you know? Moving is cool. How do you explain that? So you'll have an experiment that will be the first. Then your reaction will not be happening in that end. They just began in that. You have to maintain the reaction throughout in that element. So that vacuum as in is vacuum cold? I mean, if you take out radiation and isolate enough, will be cold. Yeah, but there is you will just want to put it in a black box that will not cool it to 10 to 1. What if we use lasers to heat them up? You don't want to heat them, you want to cool them, you want a problem. No, but you give them lasers in specific orientation to reduce the energy of the one. It's kind of laser cooling. Essentially, yeah, and then you're going to you're going to induce the reaction. That's not what you do. I mean, has nobody heard of supersonic expansion? No. You can just expand the gas from high pressure to low pressure. If you do it in some orders of pressure, the gas will expand using its own internal energy, right, in a pressure gradient, and the temperature will drop. Now, if you do it simply from like a high pressure chamber to a low pressure, that will do the same problem. The temperature will drop suddenly, everything will start sticking to your wall. Not have that. So what we are going to do is we put these things through, and that's where it brings us to our first technique. It's called crescent or Hesu in French, where it was made. It has a French full form. I'm not really saying that. So it came up in the 1980s in Rennes, right where I was. That's where it was made. And Creto is one of the most widely used techniques in terms of creating these low pressure environment where there are enough collisions. Another problem is even if you go to lower pressure, you have to maintain a number density so that there are collisions and reactions. So so you do a supersonic expansion, but you don't do it through a hole or just expand it into another chamber. You do it through a specific kind of a nozzle, which is like a convergent divergent nozzle. Converges first and diverges then. That's the nozzle. That's called a label nozzle. And the gas is stored in a reservoir that is here the left, right for you is in the red, which is in a high pressure, high room temperature environment. And then and this is the pressure chamber itself is formed out using the industrial scale forms that drops the pressure really low. And then this expands from the reservoir to the throat where it's a supersonic speed. And then it creates a flow. So it creates a flow which can be characterized almost exactly in terms of temperature and pressure throughout the this flow will not stick to the walls of your pressure chamber because and you can alter its diameter, the diameter of the flow and the core according to what kind of nozzle you're using. So this makes a wall-less reactor. There is no wall to this. All your molecules are confined within this flow, and the reaction will proceed within the. Another advantage of having a flow is that you want to measure kinetics, and you have things that are moving in time. So you will see how it will make it easier later on to actually measure that. So a lot of problems to answer each pressure. And like I was saying, so basically you have a buffer gas like helium, gas like helium, and then you inject your reactants within the reservoir and just let it expand through this level nozzle to get a each of there's not one level nozzle, that's a resin freely printed level nozzle. There's actually a bunch of different materials. Each one is specifically designed for what your carrier has. There's argon, there's helium, then each one has a specific size of the flow and also the temperature you can go down. Yeah, so these are all the nozzles that they have, and all of these are first they were first simulated. Each and every nozzle was first simulated with fluid dynamic calculation. Then they have separate apparatus to check how well their flow is going. So this is yeah, so this is how a pressure flow is made. So now we have the conversion. So we move to the next part of our process, which is sensitive detection. We need a highly specific method that should be able to differentiate between things like isotopes, isomers, conformers, and it should also be stable and repeatable, obviously. And now, so any guesses at this point? What kind of method would you start to detect molecules? What are the commonly used methods to detect molecules? Mass spec is a good answer, but it's not used here. Mass spec is used for some experiments with decrease, but it's not decrease. In fact, the hint is in the name. It's a special church. I doubt you'll know, but the church stands for the detection. It is spectroscopy. It is optics. You're right. It's, if you can call it the microwave optics, it is. You have to measure it while the reaction is happening with extremely high sensitivity. Yeah. You'll know in 5 minutes. I mean, I want NMR and I want mass. Other spectroscopy. Infrared. Infrared. Sorry, I didn't hear it. Infrared. Yeah. Okay. It is a let's move on and look at the electromagnetic. But okay, so microwave has rotational transitions, the infrared has rotational transitions, the ultraviolet and the visible usually have electronic transitions. If you want to make a guess, what kind of spectrometer should this be? It's actually easy, doesn't it? If you know how data is collected through observations in astronomy, you could make a guess. Which region does the data come from in astronomical observations? What is the most common, right now I have to tell you, name the most common type of telescope you know. What is the radio telescope? Just wait. What are they're not actually radio, they're not just radio. Microwave. The definition of the radio wave to a radio telescope is actually different. You can Wikipedia. Okay, I'll stop messing with you guys. It's second year mostly. So it's basically what we are looking. Yeah, we do go up to like we can go up to near IR in data in the way that data is collected. Okay, we're going to stick to microwave rotational spectroscopy. Mostly because rotational spectroscopy tends to be much more sensitive than say vibrational spectroscopy. Vibrational spectroscopy arises from bond vibrations, which is how these bonds are vibrated. And bond vibrations are not really specific to the structure of the molecule. Right? Bond vibrations are not really specific to the structure of the molecule. But if you look at the energy levels in rotation, so the energy gap depends on like the rotational constant B for those who know. And this B has a moment of inertia term inside. Now, moment of inertia is what? And what is moment of inertia thing? I'm sorry for making this a test. It's really fun. Tell me the formula. I told you that what distribution of mass. It's not just dependent on the mass of the molecule. So distribution of mass. So if you have some you say isotopes, the mass change. So rotational spectroscopy can, in a sense, so if you do a good enough technique, sensitive enough technique, it can differentiate between isotopes, even if between conformation or isomers. That way, the mass distribution will change, right? So this technique is specifically in the microwave region. It is also known as mmWave. Wavelength is in millimeters. So this technique is called the Church pulse Fourier transform milliliter wave spectroscopy. I will not explain most of what the name means. I'll just explain what Church means because he asked. Yeah, so this is the microwave region for rotational spectroscopy, which is pretty sensitive compared to some other regions of the electromagnetic spectrum. It also lies within what radio telescopes pick up. So it will be easier. So there are already established channels between observers and laboratory spectroscopists who kind of confirm what molecule is good there or going. So it makes it convenient to work in this system. And so this is a broadband because you want to find so spectroscopic techniques can be of several kinds. You can go with like one specific frequency trying to find one thing, and that's it. You need that. But what we need is really what we call a broadband technique because we have like multiple isotopes we want to detect simultaneously. So it's better to go with a technique that will cover a frequency range, not just like a broad frequency range. How this is done using a chirp. What a chirp is the signal that increases in frequency as it increases with as time passes. So it's pretty easy to see. So if there were sine waves, you see the frequency kind of slow in the beginning and then it speeds up as you go ahead. That's a chirp. It has multiple frequencies. And each molecule will have a different excitation frequency that it will occur. You will be able to detect all of them simultaneously, which is what makes this an ideal technique for measuring branching ratios. So once what the spectroscopy actually looks like, you have these gas molecules that are formed. You put a chirp, and the chirp will align all of the chirp will align the dipoles in a certain direction. It will force them into alignment. And while they emit this energy, as what is known in the time. If you look at this in the time domain, you see energy being emitted as a free-induction decay and FIT, which if you take a Fourier transform, simply corresponds to the frequency that it had absorbed at some point. So using so-called Fourier transform millimeter wave spectroscopy, you can set up a very sensitive. Now, what this actually looks like is to table the film. This is the spectroscopy.
Does the decay correspond to one particular molecule of the species or just the whole?
The decay will look different depending on how many different types of molecules there are.
One molecule absorbs the frequency, and then the basis of energy action. Will one molecule decay the energy first time look like that, or is it for the whole an amount of molecule?
An amount. For an amount of molecule. In fact, if you have one molecule, the decay will be so little, you won't be able to see. All of these molecules are in phase, so they are emitting out of they're all in the same direction. They lose alignment, lose it together. So that's why you see this intensity. They'll all be in phase. Their emissions will be in phase, they'll add up, and you'll see a significant decay. Because one molecule will be so little, you won't even be able to do it. So yeah. Of course, we'll get to that. That's true. So that's a question somebody who knows spectroscopy would ask. We'll get to that. The roundabout, we'll get to why it was. So, so this is what, so in the microwave region, if you look at the electromagnetic, not all regions can be generated and detected in the same. So up to the microwave, the radio wave, to the microwave, we do something called electronic generation. That is simply using electrons. You start with a, AC, small AC current, and then you can step it up using mixers and reach to frequencies in the micro. But you can't really do that IR and there you need optics to generate. So the electromagnetic spectrum is not like consistently generated in it. So for us, it's good. It's electronics. You switch them on. They start working immediately. I work in optics. They don't work at. So yeah. So this is what it actually. This is the transmitter. There's the things being transmitted here. So the electronic signal is stepped up to the point that it becomes an electromagnetic wave when it's electricity propagates through space. And then you have a wave guide and then the microwave horns that project it into the flow. So this is what the crystal essentially looks like. You have a larger nozzle, you have molecules out there, reactions happening, and then you have these are the microwave horns I was talking about. Those two tables are on both sides of this thing. One side you emit the church, the molecules absorb it, you switch off the church, you wait for the molecules. Everything is really fast. You still have to you switch off your church. The FID comes, record it using take it using the other horn, and then you step it down again to AC frequency so that you can record the data on your computer. So this is what the crystal is.
When the molecules are like moving along that speed, is it you do the church?
You do the church first. Then you switch off the church. And then the molecules start emitting the and you record that.
Right. But isn't you saying that the same molecules that are going to be in that part of
the molecular FID emission is at the scale of micron. The flow is not a micron. It's not as in
okay.
There is an area. So
it's like it's not much slower. Same molecules.
Yeah. To some extent, I guess, but I think if you look at the time scale, it's fair. Because this flow is obviously not going to, all the molecules are not going to move away immediately in like a microsecond time. But the FID is immediate. Good as well, and the energy will immediately in microseconds. Like it lasts a microsecond, but it immediately starts everything up. It's really, the time scales are not moving. So, yeah. now it's question time again. No, wait. You first get to see the whole setup. This is what it looks like. So that's the crystal chamber. There's a movable reservoir where you fill your gas. Behind that is the crystal chamber which has been pumped out. Actually, the pumps are not here. They are floor beneath. There's a hole in the floor. Through the hole in the floor, there's a valve which is being used to pump out the chamber direct. There is a level nozzle between the reservoir and the chamber. And then the horns, the spectrometer, which is on two tables essentially, is mounted. You can see the transmission side is here, and there's the receiver side. And then there are these waveguides and those microwave horns. They look exactly like that, by the way, they're super golden like. And they emit from one side and then receive it from the other side, and then there's this electronics there. So this is what the researcher of the planet is. It looks like in real life. It's huge. It doesn't look so huge. Now, moving on. Question time again. Is tracing perfect? Obviously not, because I'm asking you this. Also, because no technique really can be. But if you were to think about some problems with whatever I've disclosed, what would you? He told me a problem. What about non-polar molecules? The way rotational spectroscopy works is that it can only detect molecules with a dipole moment. If you don't, so essentially you can't actually detect the gene because it has no dipole. That is one problem. Anything else that you can think of? Firstly, if you go to very low temperatures, it might not stick to the walls because there's a but molecules will start clumping together, called clumping. That happens, you will lose some molecular signal anyway because this is a completely different kind. It's not a single molecule. Also, the mass change, the spectrum move, everything is moving. There are fixes to almost all problems here. Next. So, next so the reactions that can happen can only happen within the flow of the and that is limited by how long this uniform flow is held. It can't go on forever, obviously. So only reactions that are certain, that are fast in some sense, have rate constants above a certain threshold, can really be accurately measured with the pressure. That will actually answer your question. So most of the reactions that are that fast in space happen with the radicals. They are still neutrally neutral, but they happen with radicals. Common radicals are cyanide, OH, all of these have a dipole moment. And when you don't have a dipole moment, you usually use like proxy of molecules with other molecules that might have a dipole. So we have limited hydrodynamic time, so only reactions of a certain speed can be detected accurately. Then, like really expensive. You see that whole chamber has to be constantly pumped in with gas to do multiple reactions. And these are all noble gases, helium, argon, which are like crazy expensive after the war. This is really expensive. The solution that to this is actually pulse correction. That is, instead of having a continuous pulse, a continuous flow of you would have resonant pulse. That is flow. There is uniform. It's still uniform within the flow, but it's not a flow that keeps going on consistently. We go on for some time, stop for a bit, go on a little. Within these short pulses of flow, however, conditions can be controlled, like continuous. In fact, most of the other setups around the world of Creso are called Creso because they're more recent. They were one of the first places to have Creso. So they kind of invented it. So it's still a continuous method. Now, fourth is that the pressure, we do drop the pressure, it is still a little too high. The problem is definitely much higher in orders of magnitude than space. So there are two ways of going. So you might say that what's the point of looking at PDI? Usually choose reactions that don't have very strong pressure. So it doesn't matter if we are a little higher in pressure. But the problem with pressure really is that if you have molecules, too many molecules at high pressure, they'll collide with each other. They'll butter each other's energy. Your lines that you get at the sharp frequency, the spectrum, will broaden. This is a problem when you're looking at closely spaced ice. There's no resolution of your will die. You won't be able to tell if there are two isomers or one. So the way to solve, they have solved that and actually by introducing a secondary expansion chain. So you are seeing the reciprocal now. I will line a little bit. The microwave horns are not really in the flow. You have a pressure flow, and then there's something called a skin, which is that triangle thing there. It's basically a very fragile metallic cone of sorts. And that kind of takes from the isotropic core, goes into a secondary expansion. The reaction completes in the fluids. Products are expanded into the secondary chamber, and there is the microwave horn, where the measurement can take place in much lower. And obviously, to create this lower pressure, you have extra pump attached that you create a pressure gradient between the skimmer chamber and the flow, crescent chamber. And where you're actually measuring is in the skimmer chamber, not anymore in the crescent chamber. That is what was there in the picture as well. That's a turbo pump. That skimmer chamber. We were already in the skimmer chamber. I'm sorry for that. Yeah. So this is so you introduce this is what Presso actually looks like. Now that we have some understanding of what the texture is, we can choose the reaction and understand how kinetics are exactly meant. So, like I said, we'll be choosing a reaction with a radical relatively fast, and why we are specific. You guys want to so the specific reaction was recently observed in 2021 in the tallest molecular cloud. So this is cyclopentadiene plus the TN. And then what we have observed, there are two isomers obviously, which are very close to each other energetically. But one, I'm going to call it CNCPD, cyclocyclopentadiene. So one CNCPD is much more abundant than two CNCPD, and we don't exactly know why. So this is one of the reactions that was being pursued while I was there. And most of these reactions are actually carried out under pseudo first order conditions because pseudo first order means that you take one of the reagent much more than the other. So now the rate only depends on one of the reagents. So that makes it much easier to figure out the rate constant. And then from the pseudo first order rate constant, you can actually go and calculate the second order, which A plus B is giving you AB. So it's a second order reaction. So firstly, CPD. So CPD cyclopentadiene actually at room temperature exists as in its dimer form. So you have to first break it down and then make a mixture with say the gas or carrier gas that is helium, and you have to do the reaction not pretty quickly because otherwise you will get dimer. So you can't risk that. And now we come to the answer of what to do about clustering. You'll be like, we put it in the chamber, we put it in the reservoir for long, right? It can cluster at any point. It anyway has the tendency to form a diamond. So what you do is you actually perform a clustering test. What you see on the x-axis is density. So and then on the y-axis is the molecular spectrum intensity, the line intensity of that molecule. So as you go higher intensity, so you're increasing the number of molecules, so the line intensity, the molecular signal should also increase. Right? But at some point, the pressure is going to be too high and it's going to start making these clusters. So once it starts making these clusters, this won't be a linear graph anymore, but it's tabular. So you have to take care that you always put the CPD concentration less than when it starts to go. And that's how you go around the cluster. That is one. The other reagent is the CN radical. So now the CN radical has a problem with something. You make a radical, say you prepare a radical, then you put it in the reservoir. It will react immediately, like wherever you make it, wherever you store it, you pass it through air. It will react with something, we know radicals are fast reactions, and then it's gone. Like your radical is gone. So how do you get about? Like how do you get the radical from say your reaction place to the flow? Yeah, but while going to the nozzle, no, it's react with something else. Then there it react with there. It's react with. You make it in situ. Exactly, you make it in situ. You do so. What you do is you take a precursor, answer that question, and then you don't. You make it in situ. You don't transport it. You just take a precursor like IC, and you inject it into the, and then you photolize it with an excimer link. So along the whole path of the procedure, there is also actually an excimer laser aligned. And that excimer laser fire creates your CN radical, and the reaction starts. That way you can also measure the starting point of your reaction, which you need to actually study from. That's really a smart scheme then. Not risk killing of your CN radical, and you know exactly when the reaction starts. It's also the limiting reagent, since we are in pseudo first order. So you need to measure its concentration beforehand. You can do it with a fluid resistance test. So finally, this is the laser. So you see through the whole crescent. So you saw the temperature, there's a reservoir, there's a level nozzle, could expand through that, and then the turbo pump into the skimmer chamber, there's a skimmer in between, and through the entire path is an excimer loop, which is going to fire and create your radicals immediately. Now we can finally get to the how are kinetics exactly measured. So you have a reservoir and you create your flow with the precursor ICN and whatever the other reactant is, CPD and our case. And then there is your microwave ponds are at a fixed distance. You saw the reservoir. Right? The table was at a fixed distance from your reservoir, from the living room. So now you fire the beam and the radicals are created. The microwave fonts or the detector can only see what is in front of it at any point of time. So imagine there are four different regions of the, so there is S1, S2, S3 and S4. S4 is right at the nozzle when the laser fires. So initially the horn just see S1, which is like just right after the reaction is started. So you will see like a very little concentration of your. After some time, the flow is moving. So it will push some more molecules, the older molecules will go get out of the chamber and will push some more molecules in front of the detector. These molecules, however, have gotten more time to react. So obviously the concentration of your product will be a little higher. So when it measures S2, S2 will give you a higher concentration. Similarly, then the next step is there. And finally, you measure what was the nozzle at the base. So you're still limited by your hydrodynamics. The time you have a measurement is the time the gas that was in the nozzle comes to the detector. So that sample should have the highest one. Because you have a broadband technique, you can do these concentration measurements for different molecules all at the same time. And that's how you can know what is forming more, what is forming less. And at least you can get a relative abundance of multiple molecules that are forming at the same time in the same condition. So yeah, that's how rate is measured if you're successful. This experiment is not yet successful, it's a work in progress, but the formation of HCN is very easy to do. So what you're actually seeing is that you see the line intensity at 8861.847 gigahertz, which is HCN line, is slowly increasing in intensity, and that intensity has been plotted. Time zero is marked by your laser pulse when your laser fires. And then slowly the concentration of HCN is the line intensity. The concentration is increasing. At some point it will go and it will, at the end of hydrodynamic time, it will tap out. Because you have exhausted, you have chosen a fast enough reaction. At some point you'll exhaust your reactants. So like this, you can measure gate kinetics, you can also measure branching rate. HCN is common. They also measured HNC, which is what we began. That's how they could continue while we see more HNC at lower dosages. So yeah, thank you. Done. I hope you like it. I had a conclusion to make. I did say for that, but that was a little lack. I am really sorry for what Carol you guys. It's really fun to me. So, no. I'm concluding the document. Easier to what you write. So these are the people I work with, but they're not the writing girl. So okay, bad to say don't read after I wrote it up, but that was the professor I worked with. If you were to make a guess, what department do you think is working? How many seconds? No, not chemistry, okay. Okay, then there is no SCS, okay? How many say chemistry? Okay. 1, 2, 3, 4, 5, 6. How many say physics? Did you read it? Okay. How many say like, okay, fine. I excluded that one. There's no, it was not the department. I think it was the Institute of Physics. The Department of Molecular Physics. Okay, what degree? So this is my professor. And I want to guess. Want you to guess his what discipline do you think he has a PhD? This is the person who's doing this. It's his brain cell. Guess it. Come on, I've been asking questions all presentation. These are easier than what I was asking. There is no PhD in instruments. Physics. Physics.
Biology.
So you think
Humanities.
come on, yes, anything. Okay, this year. How many say physics? Kidding around, come on, hurry up. This is chemistry. How many say chemistry? Why do you think chemistry? Astronomy. Please, be good. No, he didn't.
Economics. Economics.
The reason, okay. This is the postdoc who was. Do you think he has a PhD? He identifies with the chemist. He does not identify. But a very nicely thinks of himself as one of the fine, but I'm kidding around. The point I want to make is that this kind of work is what we call truly interdisciplinary. Everybody I met there was in a physics department, but most of them are working with us. Ian has a degree in chemistry. Alberto also has a degree in chemistry. Miriam also is a chemical engineer. So what I really want to put out there is, as you work here or as you live in India, to grow and make up these notions of this subject is this, subject is that. Because I'm a chemist, I will not see. Because I'm a physicist, I will not see. It makes no sense. It's bullshit. There are subjects that lie at word. Yeah, I said bullshit. So it's all absolute.
Monetization kicks in.
You have been that it's a personal experience that I yeah. The idea that I'm trying to share here, instead of being limited to what department I am in, and so that I should never have applied to an institute of physics. Right? And then they should not have hired a person in the chemistry department to become a professor. In fact, most of the people I have worked with in my internship are all people with degrees in chemistry and working in physics. I don't know why. But that's how it works. All vice versa. So the idea I'm trying to say is that there must be people like I was really confused when I was in my second year about whether I want to do physics or chemistry because I thought they were incompatible. The idea is that there are multiple fields that you can access that are really right in the middle. So you don't need to have a regret about life. You can just take up questions that are interesting to you and approach them the way. So, I mean, fluid dynamics simulations definitely don't come in chemistry. But the thing is that science does not sit and ask, कि अच्छा, I belong to chemistry, I'm a question, and I belong to chemistry, so only chemistry can answer. Or I am a question that belongs to physics, so I shall only be answered by physics. That it doesn't work. So if you are confused or if you really don't know where to go, there is always a way. You just have to look for it. There are fields that lie right in the middle of subjects, and it's much more open when you move out of the country than when you're. So don't. All that's important is to not have close movie. I think you have fun with science. That's how I want to conclude this. Good.